Welcome to part 2 of our first pre-calculus online lesson. We're still talking about cosine waves, sine waves. If you're starting from here, don't. Part 1 should be around somewhere. Find that one first. In part 2, I want to pick up right where we left off. We had found that sine waves look like this. They start in the middle and go up, and cosine waves start at the top and go down. So one of the things that I want to say about this, first of all, is I'm going to use the word start and end very loosely here. In the first video we talked about how these things are periodic. They repeat these shapes forever in both directions, so there is no start, there is no end. I'm using these words very colloquially, very casually, to represent what it does on the axis and when it finishes one period. That's what I mean by start and end. Harley, what is your deal? You want picked up again? Okay, here's Harley again. She's mad about something. Who knows what? Yes. So, I'm going to use the words start and end very loosely. That shouldn't be a problem. I think that they're very useful words. They're very helpful words to understand this topic. So that's what start and end means. Know that these functions are infinitely long. So the thing I want to talk about today is both of these functions are bounded top and bottom by 1 and -1, and both of these functions will cross the axis infinitely many times. That's just a thing that happens. So of course, I want functions that will reach +4, just as a random number I picked that's bigger than 1. I want functions that will be that big. I want functions that will reach -10. I want functions that will never touch the axis. And I want functions that will never touch 1 or -1. So today we're going to talk about how we can do that. I'm going to start with sine and cosine functions that can hit 4. Your standard sine and cosine function are bounded top and bottom by 1 and -1. That's just the biggest and smallest they can be. So if I want a function, if I want a wave function, it's going to hit 4 or bigger numbers like 5 or 10 or 12. I want to make this thing bigger. So we're going to make it bigger. We've talked before about how to stretch functions, make them bigger, smaller, wider, before. So in the past, we would call this a horizontal or a vertical, a vertical stretch. 4x taller. That's how we can make a sine function hit 4. You take your sine function, you stretch it 4 times taller. Yeah, take your sine function, stretch it 4 times taller. Now you get a sine function that hits 4. Unfortunately, mathematicians, being a pedantic and feckless lot, have decided that the word for doing a vertical stretch to a sine wave is going to be different from the word for doing a vertical stretch to literally any other function. So instead of calling a vertical stretch, we're going to call it the amplitude But it works functionally exactly the same as a vertical stretch. We can say that we want y to equal 4 sine of x, and we will get a sine wave. Here's -1 and 1. Dotted green is our standard issue sine wave. Here's 4, here's -4. Solid green is that sine wave being 4 times taller. If you want to check this out with a table of values, do it. You have a unit circle at your disposal. You know how to multiply numbers by 4. I trust in your ability to verify this on your own if you feel so inclined. I do want to officially define the word amplitude though, because there's a little bit of weirdness in some niche cases that will come up later. Amplitude is no, I lied. I don't want to define amplitude right now, because my definition of amplitude is going to rely on a different topic that I haven't talked about yet, so I'll come back to that. We'll define amplitude in a minute. Okay, so next order of business is I want a sine wave that never crosses the x-axis. Standard issue sine wave crosses the x-axis approximately infinitely many times because it's periodic. It just does it over and over and over and over again. I want a sine wave that never does that. So stretching or shrinking this is not going to help. Moving it side to side is not going to help. The only way you can get a sine wave that never crosses the x-axis is to vertically shift the entire wave above the axis. And again, before we would call this a vertical shift. And again, we're going to be doing a vertical shift, and it's going to function exactly like all the other vertical shifts we've ever done, but we're going to give it a new name. The new name for this is a midline. It's called the midline because it's in the middle. It's the line that's in the middle of the wave. So usually the axis kind of goes straight through the middle of the wave. In this case, if we're moving it away from the axis, we still want to have a line that sort of goes straight through the middle, and we're calling it the midline. So we can get this by looking at something like y equals the sine of x plus 2. I like to draw the midline as a dotted line. That helps me out. So if it's sine of x, the amplitude here is 1. So from this middle line, it's going to go up to 3 and down to positive 1. It's going to do that over and over. Whereas our standard sine wave did this. So it's the same wave moved up 2 units to give you a midline of y equals 2. From y equals 2, this particular sine wave will go up to 3 and down to 1 because the amplitude is still 1. Things are going to get exciting when we start doing multiple of these transformations at the same time. So if we look at something like y equals, let's say, 3 sine of x plus 5. Now we'll go minus 5. It would be reasonable to ask, does this sine wave touch the x-axis? Let's find out. I know what a sine wave looks like. I know that this is the midline and that this is the amplitude. So I'm not going to make a table of values for pretty much any of these. It's like we talked about when we did exponential and logarithmic functions. The goal here is to be able to look at the transformations on the function and figure out what the graph looks like based on those things alone without making a table of values. So I will write down that the amplitude is 3 and the midline is y equals -5. So here's my axis, 1, 2, 3, 4, 5. -5 is going to be my midline. From here, I need to figure out how high the thing goes and how low the thing goes. And that's going to come from the amplitude. This 3 means that it's going to move 3 units above this line to get to its peak. And it's going to move 3 units below this line. Oh, that was only 2 units. It's -5, 4, 3, 2, yes. -2 will be the peak value of the sine wave. -6, 7, 8 will be the smallest value of the sine wave. And you can find the exact coordinates of these points. I know that this thing is going to peak at pi over 2. That's what sine waves do. This is pi. It's going to hit its low point at 3 pi over 2. And it's going to come back to the midline at 2 pi. So this is the basics of how we're going to be graphing transformed sine and cosine waves. I want to mention here that the sine waves and cosine waves function in pretty much the exact same way. They both have the same amplitude issues, the same midline issues. I should say, you handle midline and amplitude exactly the same for cosine and sine waves. The difference between a sine wave and a cosine wave is sine starts in the middle and goes up. Cosine starts at the top and goes all the way down, and then back all the way up to the top. So all of these examples I'm going to use are going to, I guess not all of them, most of the examples I'm going to use, I'm going to demonstrate on sine waves. Just know that cosine works in exactly the same ways, just has a different start and a different end. Again, whatever start and end means. I'm going to cut this video here, speaking of starting and ending.